Hello students, welcome back to JCE Connect series of lectures. So in previous class, we have solved uh, work done and efficiency of a Pelton wheel, and what is the equation to calculate work done and efficiency of a Pelton wheel. We have solved by drawing a velocity triangle, and we have derived equation also, that is for force exerting by the jet on a Pelton wheel bucket, then work done by the jet, then the efficiency, and for the maximum efficiency. This all we have calculated in previous class. So in this particular session, I'll be discussing about the design parameters and working proportions of a Pelton wheel. Means uh, if we want to obtain an optimum efficiency, and what could be the number of buckets, what could be the diameter of the runner or disc, and what is the actual velocity, and how many number of jets are required. These all things we need to calculate for getting the optimum efficiency. So that is the design parameters and working proportions of a Pelton wheel. So for that, the first thing is we need to we have to calculate the power from the turbine shaft. To calculate power from the turbine shaft, so this is the formula generally we use, that is a P is equal to gamma W into Q into H into overall efficiency, where gamma W is the specific weight of the water and Q is the discharge and H is the head available and gamma O is the overall efficiency. So from this we get the power from the turbine shaft. Then actual velocity of the jet is slightly less due to frictional loss in the nozzle and is given by V1 equal to CV into root of 2gh, because we know the theoretical velocity, that is root of 2gh, but actual velocity as water is flowing through a penstock, because of the frictional losses, uh, the velocity get decreases, and based on that the actual velocity can be given as CV into root of 2gh, where CV represents the coefficient of velocity. Generally it is to be taken 0.97 to 0.99. Then as we know and we have derived in previous class, the maximum efficiency of the Pelton wheel can be obtained when the wheel or the bucket velocity is half the jet velocity. This we have uh, proved in while doing the derivation. So U equal to V1 by 2 for maximum efficiency. Then the velocity of wheel is written as U equal to KU root of 2gh, where KU represents the speed ratio, and the speed ratio theoretically we have obtained 0.5, but it is generally 0.43 to 0.47 because of some losses occurred in the passage of the bucket. Hence the speed ratio can be taken 0.43 to 0.47. This is another working proportion. Then the next third one is the total discharge through the Pelton wheel must be equal to the discharge through the number of jets. If suppose the uh, the turbine is been running by providing a number of jets, if we want to calculate the total discharge, then the total discharge through the Pelton wheel must be equal to the discharge through the number of jets provided. So Q equal to N into pi by 4 d square into V. That is A into V, where N is the number of jets. Means if this is the Pelton wheel and these are the buckets provided, and suppose this is a main pipe, if the jets are provided here, this is one jet, and through the same pipe if the another jet is striking like this, if the multiple jets are been provided, to generate the power, and then the total discharge is equal to the number of jets provided. Okay, then the next, the mean diameter of the Pelton wheel D, the mean diameter of the Pelton wheel D, that means the wheel diameter, this one, this is the wheel, the mean diameter of the Pelton wheel. The mean diameter of the Pelton wheel D measured up to the center of the buckets, and as we know the wheel speed, that is pi dn by 60. This is the formula to use to calculate the wheel velocity, that is u equal to pi dn by 60. Then from this we can get easily the diameter, or we can call it as a pitch circle diameter, 60 into u divided by pi n. The mean diameter D is also known as pitch diameter. Then next parameter to be calculated, the jet ratio is defined as the ratio of diameter of runner, the ratio of diameter of runner to the jet diameter. This one, this is the jet ratio. Then the jet ratio, for jet ratio m is the symbol using, that is the ratio between the runner diameter and the jet diameter. And generally the jet ratio will be lying for optimum number of jet ratio should be between 11 to 15. To get a maximum efficiency, generally it is lying between 11 and 15. This is the jet ratio. The jet ratio means the diameter of runner, the ratio of diameter of runner to the diameter of jet. Then the next parameter, the number of jets in a Pelton wheel, means optimum number of jets required to generate maximum efficiency. Okay, so number of jets in a Pelton wheel, normally one, but to increase the power generation, more number of nozzles are provided, and maximum up to 4. Generally the one jet will be providing. If we want to increase the power generation, then more number of nozzles are being provided, so maximum number of jets will be up to 4. Then the next working proportion, that is the working proportions of the turbine buckets are generally in terms of jet diameter. The working proportions of the turbine buckets are generally in terms of jet diameter D. Then, as you know, this is the plan of the bucket, and this is the stem which is to be connected to the runner of the Pelton wheel, and this is the plan, and this is the central part, that is called the splitter, and this is the curved shape of the bucket, and this is the groove which is been cut at the bottom of the bucket, and the jet will come and hit at this place and the water get splits. Okay, then this B, whatever B is here is marked, it is called axial width, and in this direction whatever the length is measuring, it is called radial width, radial. Okay, this is the groove width, this is the axial width, and this is the radial width. So now in here I have taken, this is the axial width, this is the groove width, this is the radial width, and this is the depth of the bucket. The shape of the bucket I have already shown in the previous lecture, the plan as well as the cross section of the bucket. When you join two spoons together, whatever the shape you get after joining the two spoons, so that is the picture of bucket, Pelton wheel bucket. So we need to proportion these all lengths, that is axial width, groove width, and the radial width and depth of the bucket. So generally the axial width B can be taken which is expressing in terms of jet diameter. Generally it is to be taken axial width 3 times of diameter of jet to 4 times of diameter of jet. Okay, axial width for a smooth operation. So this is the axial width dimension, that is 3 times of diameter of jet to the 4 times of diameter of jet. Then the radial length to be taken, that is A, 2D to 3D, radial length. Okay. And the depth of the bucket, it is to be taken 0.8 times of D to 1.2 times of D. So all are expressing in terms of uh, diameter of jet. And one more is this one, groove length, that is groove, that is E equal to, it is to be taken between 1.1 times of D to 1.25 times of D. And also the this is 1.1 times of D to 1.2 times of D. Okay. The next proportion is the number of buckets on a periphery is decided. Number of buckets on the periphery is decided mainly on the two principles. Means whatever the number of buckets providing on the wheel of the Pelton wheel, these buckets, number of buckets. Okay. So the number of buckets on a periphery is decided mainly on the two principles. The first one is the number of buckets should be as few as possible so that there is a little loss due to friction. Okay. So the number of buckets should be optimum number, and the number of buckets are being deciding based on the losses occurring. So that's why it has been given the number of buckets should be as few as possible so that there is a little loss due to friction. And one more principle is the jet of water must be fully utilized. Whatever the jet coming and hitting the buckets of the Pelton wheel, that jet should be completely utilized by the buckets provided on the wheel of the Pelton wheel. So the jet of water must be fully utilized so that no water from the jet goes waste. Okay. So means none of the buckets should miss the jet. So all should get utilized, the whatever the water is coming through the penstock and through the nozzle, that should be utilized completely. That's why it is given the principle as the jet of water must be fully utilized so that no water from the jet goes waste, that is no water escapes without striking the buckets. Means all whatever the jet is coming and hitting the bucket, all should receive the jet. Okay. So based on these two principles, the optimum number of buckets are given on the Pelton wheel. This is the Pelton wheel. These optimum numbers, how many numbers to be provided? Okay. So jet coming and hitting. Okay. Then the optimum number of buckets should be given, that is Z is equal to 0.5 times of M plus 15. 0.5 times of M plus 15. Okay. So by using this one, we can get the optimum number of buckets. Okay. So that these two principles can be satisfied. That is, the first principle is the number of buckets should be as few as possible so that there is a little loss due to friction. Then the second is the jet of water must be fully utilized so that no water from the jet goes waste, that is no water escapes without striking the buckets. Okay. And remember this formula, that is Z equal to 0.5 M plus 15 to calculate the number of buckets. I hope you understood these working proportions. And the next class I'll be solving a problem that is on a velocity triangle as well as the design problems. I hope you understood these things. Okay, we'll continue next class. Thank you.